All right, welcome ladies and gentlemen. This is video number 5, and this is our final video in our moles reaction and stoichiometry unit. In this video, I'm going to be talking about this word that you've probably heard me say a lot in this unit called stoichiometry. Exactly what does it mean? And it all really comes down to this idea of mole-mole ratios. That's really all it is. So first of all, mole ratios. To introduce this idea, I want you to think about this recipe. So we want to make 20 cookies, and for that we need 1 cup of flour, 4 cups of eggs, 2 teaspoons of salt, 3 ounces of butter, and 12 ounces of chocolate chips. But what if you don't want to make 20 cookies? What if there's more than 20 people in your class, right? What if we're talking about our Regents chemistry classes that are larger than 20 people and we want to make 30 cookies instead? Well, now you've got to change your recipe. You can't use the same amounts, but you need to use the same proportions. So if we want to go from 20 cookies to 30 cookies, we want to keep this ratio of 20 to 30. We know that our proportions for everything in the recipe are going to have to, we're going to have to change it by going from 20 to 30, or a 2 to 3 ratio, right? If we simplify 20 to 30, it becomes 2 to 3. So in order to work out how much we're going to need to make 30 cookies instead of 20, we want to pay attention to this sort of 2 to 3 ratio, which is if we divide each one by 2, we get a 1 to 1.5. So we want to multiply everything by 1.5 to get the correct ratio. So instead of 4 eggs, if we want a 2 to 3 ratio, we're going to want, 1 cup of flour. We'll start with 1 cup of flour. Instead of 1 cup of flour, we want to now multiply, we want to do a 2 to 3 ratio, so times 1.5, we're going to have 1.5 cups of flour instead, right? We sort of increased it. We went from 20 to 30, so 2 to 3 or 1 to 1.5. For 4 eggs, instead of 4 eggs, now again, we want to change the amount so that we keep it proportional. So we want the 2 to 3, or multiplying it by 1.5. Now we're going to need 6 eggs. With the 2 teaspoons of salt, again, keeping this idea of a 2 to 3 to increase it, now we're going to need 3 teaspoons of salt, right? 2 to 3, start with 2, now we want 3. 3 ounces of butter, well, we can't use that anymore because we've increased the amount of cookies that we're making. So now we're going to need 4.5 ounces of butter. Again, I'm just keeping with this 2 to 3 ratio, or multiplying it by 1.5. And 12 ounces of chocolate chips. Well, we can always use more chocolate chips, right? More chocolate, the better. So instead of 12 ounces, now it's going to be 18 ounces of chocolate chips. Again, using a 2 to 3 ratio, or multiplying it by 1.5. Well, what if we don't want to make 30 cookies? What if we now want to make 10 cookies from our original recipe, which is up here? What if we don't have that many people, or if I'm just making it for like me and my husband? We don't need 20 cookies, so we would just want 10 cookies. Well, now with 10 cookies, now we have a 10 to 20 ratio, right? And to work out what that's going to be mathematically, if we divide both sides by 10, it simplifies down to, 1 to 2, i.e. now we're going to divide everything by 2, right? Because we went from 20 cookies, but now we only want to make 10 cookies. So it's literally half, right? It's half as much. So I'm going to cut everything in half. So instead of a cup of flour, I'm going to use half a cup of flour. Instead of 4 eggs, I'm going to use 2 eggs. Notice I'm keeping sort of the same total proportions. I'm just cutting all of the proportions in half. 2 teaspoons of salt is going to be 1 teaspoon of salt. 3 ounces of butter, cut that in half. That's 1.5 ounces of butter. And 12 ounces of chocolate chips. Well, honestly, I'd probably still use 12 ounces of chocolate chips. But if we're keeping the proportions the same, I'd use 6 ounces of chocolate chips. Because this way I'm keeping the proportions intact, but now I'm changing sort of the total amount. So it's still the same proportions, but I have to pay attention to how many cookies I want to make and vary the recipe accordingly. Well, why am I talking about this? Because this is the exact same idea of this thing called stoichiometry and ratios. Basically, it's all about ratios. And in chemical reactions, you can kind of think of them like recipes. The chemical reactions are telling you what the correct ratio of stuff is. It's saying that for every 1 cup of flour, you need 4 eggs. Well, it's like saying for every 2 moles of hydrogen, you make 2 moles of water. But for only 1 mole of oxygen, you make 2 moles of water. So it's telling you proportions. it's the recipe for the chemical reaction. And how do we find these ratios in a chemical reaction? Coefficients. The coefficients in a chemical reaction tell you the mole ratios between the substances in the chemical reaction. Coefficients, big numbers out in front, they tell you how many moles is our big unit in chemistry, of each species are necessary in the balanced equation. The coefficients are basically telling you the recipe for the reaction. And if you want to make a different amount of something, you have to keep to the same proportions in the original recipe. So stoichiometry is really the sort of the definition of it is simply saying, hey, what's the ratio between things in a balanced chemical reaction? And let's use that ratio to bear this in mind whenever we're talking about the reaction. That's really all stoichiometry is. So what do I mean by that? We have this chemical reaction for the formation of water. And the coefficients here are 2 in front of the hydrogen, a 1, because remember it's an invisible 1 in chemistry, an invisible 1 in front of the O2, and a 2 in front of the H2O. What does that mean? It means that you need 2 moles of hydrogen, because that's the coefficient, to combine with 1 mole of water, because that's the coefficient, to make 2 moles of water. That's the coefficient. That's what this is saying. It's saying that hydrogen and oxygen are related in a ratio of 2 to 1 because those are the coefficients for hydrogen and oxygen. They are in a 2 to 1 ratio. That if you want to run this reaction correctly, you have to always ensure that no matter how many moles you're starting with, you're going to have double the amount of hydrogen as you do oxygen. And it's saying that hydrogen and water are in a ratio of 2 to 2 because the hydrogen is 2 and the water is 2. Or you can simplify it down and say that they're in a ratio of 1 to 1. That's saying that no matter how many moles of hydrogen you're starting with, if this reaction is running to completion, you're always going to be making the same amount of moles of water. If you start with 7.5 moles of hydrogen, you're going to make 7.5 moles of water. It's the proportion, right? They're in a 1 to 1 ratio. And even though stoichiometry is this really kind of weird sounding word, that's really all stoichiometry is saying. It's just saying that we can get the correct ratios of the reactants and products from looking at the coefficients. And we have to bear those ratios in mind as we are considering the math of the chemical equation. That's all stoichiometry is. So why is stoichiometry important? Stoichiometry has a lot of uses beyond just a chemical equation. But it is important in a chemical equation. For example, we can predict how much product we can make if we're starting with a certain amount of reactant. Like say in your lab, the ratio of a reaction is maybe 2 moles to 1 mole, but maybe you don't have 2 moles, maybe you have 20 moles of a reactant to start with. You can predict that you're going to make 10 moles of product. Now this can be very useful in industry because in industry you want to make a certain amount of product in order to meet the consumer demand. So you need to know how much stuff you can make. Stoichiometry allows you to do that. Stoichiometry allows you to make that prediction. And the idea of stoichiometry goes beyond chemistry as well, because any form of manufacturing is going to be based on buying the correct amount of starting material to get the correct amount of ending material. If you think of cars, there are ratios of stuff in a car. There are 4 tires per 1 car. So if you're at a car manufacturing plant, you need to be able to order enough tires to create the number of cars that you need to sell to meet the demand that's out there. And this is fundamentally stoichiometry, this idea of correct ratios of things. Recipes, the example that I just did. It's seldom that you're going to make a recipe for the exact amount that it originally calls for. Oftentimes recipes are maybe too small or they're too big, and you need to change the proportions. We've got to keep all those ratios intact, just like I did in the first example. That is an application of stoichiometry. We're going to be looking at it from the context of the chemical reaction, but this idea of keeping the ratios intact, this is a pretty common thing. So something to remember. The coefficients, they stand for moles, which means the ratio is always in the mole unit. So it's not in grams, it's not in liters. The big number out in front is telling you how many moles of that thing are reacting with how many moles of something else. And that also means that the ratio of the coefficients is actually a conversion factor between chemical compounds, but it's a conversion factor in the mole unit. So it's not converting grams to grams, it is in fact converting moles to moles. So just an example to sort of a warm-up with stoichiometry. So given this reaction right here, 2H2S plus 3O2 goes to 2SO2 plus 2H2O. This is the reaction that we're starting with. The 2 out in front means 2 moles. So 3 moles of O2, 2 moles of SO2, 2 moles of H2O. Well, what if we started with 6 moles of oxygen instead of starting with 3 moles? We want to fill in the rest of these lines. How many moles of these other things are we going to have if we're starting with 6 moles of O2? Well, we want to keep this 2 to 3 to 2 to 2 ratio intact. So what did I do to go from 3 moles to 6 moles? I doubled it, right? I doubled the amount. So if I'm going, if I now want to work out how much H2S I need to start with, if I'm starting with the 6 moles of oxygen, I'm going to apply the same proportion. So instead of 2 moles of H2S, I must be starting with 4 moles of H2S. And same idea, what did I do here? Well, I doubled this. That means I'm going to have to double this coefficient to get 4 moles of SO2, and then same thing here, times 2, so 4 moles of H2O. So this is sort of the key. If I'm starting with a different amount, I have to keep the proportions of the coefficients intact. So I'm going to apply the same change to everything else. And then just a different problem down here, it's the exact same reaction, but now I'm starting with a different amount in a different compound. So what if I'm starting with 8 moles of H2S? Again, I have to keep the 2 to 3 to 2 to 2 ratio intact. So what did I do to go from 2 to 8 moles? Well, I quadrupled it, which means I'm going to need to quadruple everything else to keep the ratio intact, right? Keep the same proportion. So this is going to be 12 moles of oxygen, 8 moles of SO2, and 8 moles of water. Because, I mean, when you do that, look at these numbers here. This is 8 to 12 to 8 to 8 moles. This is the exact same thing as the ratio between the coefficients of 2 to 3 to 2 to 2. It's the same. It reduces down to this. So I've kept the proportions intact, which is crucial. Now, an example of a mole-mole problem where we're not maybe trying to figure out everything, but we're only looking at a small reaction. Given 5 moles of A, determine how many moles of B are formed. We can absolutely do this with the T-chart, and that's what I'm going to show you now. So we have this reaction, 2A goes to 3B. The coefficients are the critical thing. They're telling you that 2 moles of A needs to react to produce 3 moles of B, aka they're telling you the ratio between the things is 2 to 3. And if we want to solve this problem using a T-chart, we're going to use the same process that we've been doing with T-charts all year. We're going to put the moles that are given in the problem, so the problem is right here. These are the moles that are given. That's the number that's in the problem. We're going to put that in the top left-hand corner. And then the conversion factor that we're using is the conversion factor from the coefficients in the chemical reaction. This 2 moles of A to 3 moles of B. That is our conversion factor. So solving the problem using the T-chart method. First step, draw the T. Second step, put the number the problem gives you in the top left-hand corner. So the number the problem gives me is 5 moles of A. It's really critical that you include this. Don't just say 5 moles. 5 moles of what? Because in this problem, we are turning moles into moles. So we're not turning it into something like grams or liters, but we're turning moles of A into moles of B. So say moles of A, say moles of B. So then what do? Well, we want to take this unit that's here and we want to drop it down here so that it will wind up canceling out, right? Something that's top and bottom will cancel. So I'm going to put moles of A on the bottom, and I'm turning it into moles of B because that's what the problem is asking for, how many moles of B. So that's the unit that's going on the top. And then the numbers out in front here of this, on the right-hand side of the T-chart, that's coming from our coefficients, which I'm just going to abbreviate like that. So then I'm going to look, what's the coefficient for A? 2. So 2 moles of A. What's the coefficient for B? 3. 3 moles of B. So again, this conversion factor is kind of being plugged in right here, this 2 moles of A to 3 moles of B. The nice thing about T-charts is you never have to think about what is it that you're multiplying or dividing in terms of a proportion. The unit conversion will let you do that on your own. So then we're solving our T-chart. We multiply across, so 5 times 3 is 15. Then we divide by the number on the bottom, so 15 divided by 2. That's 7.5. 7.5 what? What unit have we not canceled off? We haven't canceled moles of B. So that's the answer. And then if we think about that, that makes sense because the coefficients tell us that it's a 2 to 3 A to B ratio. And we started with 5 moles of A and we want to make 7.5 moles of B. We're keeping that 2 to 3 ratio intact with the 5 to 7.5. An example, and to end this video, we're just going to have an example with a real chemical equation, giving the following balanced equation: Sr plus 2HNO3 yields SrNO3 plus H2. How many moles of hydrogen gas will be produced by 1.37 moles of HNO3? Again, it's about ratios, but we want to identify the ratio we want to use here. So it asks for moles of hydrogen gas. So where's hydrogen gas? Oh, hydrogen gas is right here in the chemical reaction. It will be produced by 1.37 moles of HNO3. So where's HNO3? HNO3 is right there. Okay, so that's the ratio that we're looking for. The 2 HNO3 to 1 H2. 2 moles of HNO3 to 1 mole of H2. First step is to identify the coefficient ratio that we want to use, because there's other things in this equation. There's the strontium here, we're not using that. There's a strontium nitrate, we're not using that. This problem isn't asking about that. We're going to focus on the 2 to 1 ratio. Now we can start our T-chart. So draw the T, put the number the problem gives you in the top left-hand corner. What's the number the problem gives us? It gives us this, 1.37 moles of HNO3. Notice I'm including that. Include that. Yes, take the extra 5 seconds and write that out. So then I know I need moles of HNO3 on the bottom, because that way moles of HNO3 are going to cancel out. And I'm turning into moles of hydrogen gas. How many moles of hydrogen gas? It's in the problem. So moles of H2. I know it's H2 because I found it in the chemical equation right here. And then what number is going out in front? Well, here's where I'm going to use my coefficients. And here's where I'm going to go back and identify this that I pulled out at the beginning of the problem before I thought about my T-chart. That 2 moles of HNO3, because that is the coefficient for the HNO3, will react to make 1 mole of H2, because that is the coefficient for the H2, that invisible 1. So then my moles of HNO3 cancels. What math am I doing? I'm multiplying the top numbers together, so I get 1.37. Then I'm dividing it by the bottom number, which is 2. So 1.37 divided by 2. So I get 0.685 moles of H2, which is actually in keeping the 2 to 1 of the nitric acid to H2 ratio intact, because starting with 1.37 moles gives us 0.685 moles of hydrogen gas at the end. So that's mole ratios, and we will definitely be practicing with this in class.